Morning, everyone. Our toy is called the Creepy Crawler. I'm Nick Fisher.
I'm Ellie Bradley.
I'm Clayton Walters.
I'm Bryn Chantal.
So first, I'd like to tell you a little bit about the backstory and the inspiration for our toy. We base it on the work of a Dutch mathematician and artist named Theo Janssen, who has developed a kinetic art piece. He calls it a strand-based, which is Dutch for beach creature. And from this, he developed something called the Janssen linkage, which is a set of 11 bars that is made to simulate an organic style of walking. For our initial design, we basically what we were thinking was a sort of hybrid form of motion, where we use the strand-based style legs in the rear, as you can see here, for the source of power, and then wheels in the front for steering. And we also designed it to be row controlled, as you can see with all the electronics on the inside. And then we initially imagined the chassis of it to be a sort of 3D printed skeleton frame, but that kind of evolved into a bit different form. But we initially imagined it kind of similar to like a series of bicycle frames. And there was a certain number of performance constraints, some mandated by the class, and then some that we just kind of found, some constraints that we found ourselves just on how our toy was designed. Some of the mandated constraints were that it had to fit into a 10-inch cube, and we had a budget of $60. And some of the constraints that we found ourselves were stuff like the power of the motor, which was a big limiting factor, as well as the amount of material we were allotted for the 3D printer, as well as the print size, or the cut size on the laser cutter, which also influenced the parts and the part size that we went with. Now I'd like to hand it off to Ellie now to tell you about some of the key features of our design.
Thank you. So, as previously stated, originally we wanted to do a skeleton model for the chassis, but from a manufacturing perspective, it didn't make a lot of sense with being able to make adjustments to the chassis later on in case we need to change positions of where the motor went or where the fins went. So what we instead used was 2 horizontal plates, and these plates were held at a fixed distance so that the Janssen linkages could have 2 connections to ground, which the mechanism requires those 2 connections in order to function properly. So to separate the chassis at the fixed distance, we utilized a total of 10 different fins that used interlocking finger joints in order to hold the chassis pieces together. 8 of these were located at the rear of the toy, which sounds like a lot, but that was mostly for the purpose of keeping the crankshaft in line, since the crankshaft was split into a total of 7 different sections, which allowed the crankshaft to move all together in rotation. Also, we used 2 side fins because we didn't want the whole piece, or the whole top chassis to bend forward and basically stabilize the structure of the entire toy. So for the crankshaft, it rotated a total of 6 legs, and these legs were modeled using the Janssen linkage as previously stated. The Janssen linkage is an 8-bar mechanism with a single degree of freedom. So basically, when you rotate the one crank all the way around, there will only be one position for each other point on the mechanism, and that simulates the walking motion of the leg itself. So starting at the center of the toy and going outwards, there is a pair of legs that are all in phase with each other. And as you go inwards to the out, they're all 120 degrees rotated off of each other. So that way you have 2 legs on the ground at any one time. And it basically ensures that there's enough force on each side to balance the machine so it doesn't teeter to one side or the other. It also makes sure that there's at least 2 feet from the ground at any one time. So we aligned the legs together using a D shaft and cams. The D shaft was sectioned off into different pieces, so that way it wouldn't interfere with the motion of the A-bar mechanism. And we basically held them in place with the use of snap rings. So now I'm going to hand it off to Matt to talk to you about the rest of the key features.
Thank you, Elliot. So now moving to talk about the steering system. As you can see, the steering system is located on the bottom layer of the chassis relative to the front of the whole toy. And the steering system uses 5 linkage mechanisms to connect the servo motor in the middle, and also 2 wheels on the side, along with the main body of the toy. The servo motor allows approximately 45 degree of motion on each side. Our toy uses a 9-volt battery as a power source. We also integrated a ESP32 in our design, which functions as a communication center between the user and the toy. So to be more specific, all interactions can be done using an app called Blink, so where users can create their customized surface to input their command, whether they prefer a dial to input the range of angles, or they prefer a slide bar for the angles. Once the communication has been set up between the ESP32 and the phone, the ESP32 will read in the information, the command input from the user, output to the microcontroller, which is connected to the DC motor and servo motor to realize the motion, whether to go forward or backward, or the range of motion to steer. Now I'm going to pass it to Clay to talk about the assembly model and a demo.
Okay, so I'm just going to go quickly into basically the manufacturing steps that we took, as well as how we actually put this together, both electronically and in the real world. So obviously, as we stated before, this whole idea is based off of the Jansen linkage, which now it's frozen, so maybe I won't. But either way, in terms of assembling this in a CAD model, we basically built a sub-assembly of just the linkage, and then we were able to put that linkage into the main assembly 6 times, as you can see here. And then each of these legs are 120 degrees separated from apart. So like Ellie was saying, basically this allows for the toy to be able to have one pair of leg on the ground at a time, so that way it's not kind of rocking back and forth or up and down. So that gives some stability. And then, as Ren was saying before, we have our steering here, which you can see right in front of you. And for actual assembly in the real world, we cut these pieces out of acrylic, and as Ellie was saying, these pieces are slotted together. So that allows for kind of like a clearance fit before we actually glued them in place. So it was already a tight fit, which was good, and then we kind of secured them in place with glue. In terms of the shafts, that was the most difficult part of assembly, just because they're so small and the diameter is 1/4 inch, and getting a snap ring plier in between like 2 cams is very difficult, and onto like this little groove proved to be very difficult. So the order of operations in which we put the toy together was very critical, and it actually took a couple tries to be able to actually figure out, well, do we want to go from the outside in towards the middle, or maybe the inside out. So that was kind of a learning process. And then in terms of actually manufacturing individual components, one of our biggest wins, I guess, was just being able to machine these small grooves, which are microscopic almost. But after we got those and kind of modified our snap ring pliers so that way we could fit it in this gap better, we were able to actually put snap rings on, and that kind of made the whole thing come together and reduce the amount of both friction and interference in between different parts. So that is our CAD model, and now I think I'll pass it back to Nick so he can wrap up our presentation.
as Clay was saying, we had a few setbacks while we were trying to assemble this. It was a very tedious process, and were we to have a chance to improve on this further, that is one of the main things we would like to consider, is just designing this to be more manufacturable, giving more consideration to the order of operations in the assembly process, as well as trying to make things a bit more human-friendly in the assembly process. Like he was saying, it was very difficult to try and get some of the internal snap rings attached on the inside here. It's very tight fit. And we'd also like to, if we had a second pass, to improve some of the tolerancing on some of our parts and to ensure a more a snug and precise fit. And then we would have also liked maybe a bit more of an opportunity to improve the aesthetics of it. Maybe adding some paint or some colored acrylics, and then maybe even an external shell to hide some of the electronics and wires, give it a bit more clean appearance. But, thank you for your time. Do you have any questions?
Do you want to do a demo?
Yeah, I was going to say, I can
Yeah.
actually just demonstrate how it moves. So, obviously the steering will operate like the guided project. And then in terms of the actual legs, being able to drive them, you can either use a motor, which this motor isn't really strong enough, but you can see it's trying to rotate the gears. But just to demonstrate, I can take these connections off, and then I can just rotate it by hand, so that way you get the idea of how it's actually supposed to rotate, and then we can be good.
One of the other future considerations we would have made would have been swapping out for a motor with more torque, which we didn't predict that we would need. The reason we couldn't do it for this current model was that the motors that we had that use larger torque were too big to fit inside. So in the future, we would probably do a redesign of how the chassis is set up, so there would be enough space for it.
So kind of just rotate like that, both ways. Any questions?
Yes?
Yeah, for the blink system that you used, was that the same setup as our first project, or how did you modify it?
It was basically the exact same setup from the guide project.
Even with the motor, it's pretty much the same because it's just rotating a shaft, and that's kind of how it was, except instead of a wheel, it uses the Johnson.
Okay, so yeah, nice work, and also it's very fancy that you can contribute to the interface. But I have a question on the assembly. So what do you think the biggest problem is for the assembly? Because I see, even when you are rotating by hand, it's kind of hard.
Mm-hmm.
So what do you think the main cause of that?
I think that if we were able to improve the clearance not only between each of these fins, but also iterate upon the shaft and where the actual groove on the D shaft is, so that way the spacing horizontally was better, that there'd be less friction in between each of the legs, and that would allow it to spin better.
So basically, it's imperfection on the body and also the caused by that.
Right.
So, have you ever predicted that, or because you chose this kind of fabrication method, did you predict the friction high?
I mean, with anything that has, like 50 moving parts all kind of pushing together, there's going to be friction, but I guess it was kind of hard to say, just like guessing how much it would be. I think with some like alignment and making sure that everything has the proper amount of like is fastened together and at the right amount of like torque or whatever